That's pretty straightforward. Time on the ship is delta t prime is equal to delta t times the square root of 1 minus v over c squared, square root. Delta t, the time elapsed on the Earth, is 100 light years divided by 0.99 light years per year. That's what 0.99c means, or 101 years. So delta t0, which we're going to call proper time, is equal to delta t prime. That's equal to delta t over, or times 1 minus v over c squared, square root. Or that's basically 101 years times the square root of 1 minus 0.99 squared, or 14 years. Okay, so to someone on the ship, you travel, the time that it takes to, or the time elapsed on this trip is only 14 years. Okay, and that kind of makes sense. You're traveling at essentially close to the speed of light. Now, I mentioned length contraction, right? The length of an object L is, as I mentioned, measured to be shorter when it's moving relative to an observer that's at rest. I won't go over the derivation. It's a little bit more tricky than the one for time dilation, but it's equal to what we call the proper length, which is an unfortunate name. It means, I mean, in some ways it sounds like it's the actual length, but it's the length that you measure when you're at rest with the object. But it's equal to, the length that you measure is equal to L naught times the square root of 1 minus beta squared. Okay, L naught is what you would measure if you're right next to it and not moving. But both measurements are equally valid, I guess, is what I really, really want you to get out of this when we start talking about proper length, proper time. What we mean by the proper name is when we're at rest with it, but it doesn't mean that the measurement of the shortening is any less valid. So in the previous example, if the ship has a length of 100 meters as measured in its rest frame, what is its length as seen from the Earth? Well, since it's moving away, it's L naught times the square root of 1 minus beta squared, or it's actually shrunk by the same amount of time, by the same factor, or 14 meters. So as seen by the Earth, a 100-meter ship looks like it's 14 meters. That's Lorentz contraction. This is something that we've observed. We've measured it experimentally. When we build colliders, particle colliders, like a Large Hadron Collider, we need to be able to build those things knowing that a particle moving at a particular speed is going to see that length shrink. If we didn't take into those relativistic corrections, then our particle colliders would not work. Okay. Suppose a spaceship travels with the speed v of square root 3/2 c, or 0.87 c. How much time elapses on the Earth during one-way 100 light-year journey? Well, this is kind of a tricky question, or maybe not. On the Earth, it's just 100 light years divided by the speed of light, or 114 years. On board the ship, though, you have time dilation as measured by someone on the Earth, right? Well, we've measured this already on the Earth. We can compare this to somebody on the ship. Here we're looking for delta t prime rather than solving for delta t, right? Normally we would solve for delta t, and we would look into the ship. Delta t prime is equal to delta t times this square root of 1 minus beta squared, or that's 114 years, right? It's just 100 light years away, and we're traveling at 0.87 c, times the square root of 1 minus 0.87 squared, or 57 years. This is essentially the twin paradox, right? Apparently. If you're on Earth, you send something out at 87% the speed of light. It takes 114 years to get there. If you're on board the ship, your clock only measures 57 years. Okay? Both are correct. Both are connected by the Lorentz transformation. This brings up another consequence, and there's a sheet that helps you with that, and that is velocity addition. What is the relative velocity of two objects that are racing toward each other or even moving apart from each other? Well, we can write this as, say, u is equal to, as the relative velocity, is equal to, if you have two particles, one with speed v and one with speed u prime, and they are closing in on each other, you would add those speeds, so it would be v plus u prime divided by 1 plus v times u prime over c squared. If they were moving away, you would use the subtraction, right? But you can't just simply add the speeds, right? If Galileo was in charge and you were ramming two things right next to each other, the closing speed would be the addition of speeds. It would just be v plus u prime. But you see that it's not quite that. And the reason that you can see this works is, suppose one of these speeds is the speed of light. Suppose u is a photon, and so it's traveling with speed c, right? Or suppose both of these are photons, right? If both of these are photons and they're moving toward each other, Galileo would say that their relative speed would just be c plus c, or 2c. But if you use this equation, this would be c plus c. So far so good, but uh-oh. We have to divide this by 1 plus c squared divided by c squared, right? So that would be 2c divided by 1 plus, well, that's 2, or c. So even when you have something that's traveling at the speed of light, and it's ramming into something else that's traveling at the speed of light, its closing speed, their closing speed is going to be the speed of light. If you have one of these equal to c, as I've shown in the handout that I posted online, you still do not get something that's greater than c. The closing speed is going to be the speed of light as well. Okay? That's the answer to the question that we started this section on. What happens when you turn on a flashlight at the front of a train? How fast are the photons going? They're going the speed of light. Mind blown. Okay, so for example, suppose you have two particles that collide with initial speeds of 0.9 c and 0.5 c respectively, as measured in the lab. Again, everything is measured with respect to something. What is the relative speed of the second particle as seen by the first particle? Now, classically, we would just add these together, and you would get 1.4 c, and you would get a frowny face, and minus 2. But this is clearly not right if special relativity is valid. The combined speed, the closing speed, is going to be v plus u prime over 1 plus v times u prime divided by c squared, or 1.4 c divided by 1 plus 0.45 c divided by c, or 0.97 c. You'll notice, as always, if the speeds are smaller than c, much smaller than c, then this approximates what you'd expect from Galileo. That is, this term becomes basically 0. As these speeds approach c, you get closer and closer to c for a closing speed, but you never exceed it. Okay. We can see this in the space-time diagrams as well. You know that the angle here is due to the speed of the frame, right? So this angle, alpha, is the same as this angle. This is the speed of light here. Let's consider an object at rest on the train as it speeds by the platform. And then we can ask again, what happens when you turn on a flashlight, right? How does this look on a space-time diagram when you start adding velocities? Well, if you add velocities, right, you look at how this is v over c is equal to 0.5. This is v over c is equal to 1, right? And an object at rest speeds by, and someone is running down the train at a speed of u prime over c equals 0.5. You would simply add this angle to that angle and get the speed of light. You cannot do that, right? So why does this not work? Or what's the fix? Well, you notice that we basically try to add these velocities straight across. What we need to do instead is add this velocity parallel, right, to the x prime axis, so that instead what you get when you add, if you have something that's moving at half the speed of light and you have somebody running at half the speed of light, the combined velocity is 0.8 c. You could see that mathematically or graphically by looking at the angle of the green line, right, with respect to this c, right? It'll get closer and closer and closer to the c line. Or you can see that through the addition formula. This is the reason why we look at space-time diagrams so to look at it geometrically, graphically, as well as algebraically. You use whatever you need to use in order to understand this more properly and more easily. And finally, we can start looking at, since we've seen how velocities, how space, how time are relative and are measured, we can define the same things for momentum and energy. Namely, we can define a relativistic momentum, and that is the mass times v over this square root of 1 minus beta squared, where beta is equal to v over c. That's just equal to gamma, if you remember that gamma is 1 over the square root of 1 minus beta squared, times nv, or another way to write it would be to pull out this v and have gamma beta times mc. The reason why we like this is because of where this heads for energy. Okay. What this means is that v for a massive object can never ever be greater than c. Right? If the speed starts to exceed c, in here we get a negative in the square root. Okay, so something that has mass cannot have momentum that is, or velocity that goes into the momentum that's equal to the speed of light or greater than the speed of light. We can also define a relativistic energy, and again, this is based on how we look at velocities and how they're added. Namely, we can write gamma times mc squared, ooh, that looks familiar, minus mc squared, or gamma minus 1 mc squared for the kinetic energy, the relativistic kinetic energy. That's mc squared times 1 over 1 minus beta squared square root minus 1. Okay. The reason why this is important is that we're getting at this famous mc squared part to the energy. For beta much, much less than 1, this whole term is essentially 1 plus 1/2 over beta, or times beta squared, or k is equal to mc squared times 1 plus 1/2 beta squared minus 1, or 1/2 mv squared. In other words, when the speeds are low, the kinetic energy, the relativistic kinetic energy, is what you'd expect. When they're not, it's equal to gamma minus 1 times mc squared. That means that we have to take a step back and define the total energy. The total energy is going to be the kinetic energy times what some people call the rest energy. So it's gamma times mc squared, which is mc squared plus that k, right? So there's an energy that's due to motion, and then there's an energy that's due to the mass of the object. Sometimes we write this as the relativistic mass. Sometimes we talk about the total energy. Depends on basically whose convention you're using. But this is where this famous quantity E equals mc squared comes from. If you're at rest in a particular frame, the kinetic energy clearly is zero, but that doesn't mean that the energy is zero. There's still energy contained in the mass, and that's equal to mc squared. Furthermore, we can write this in terms of the momentum, so that the energy squared is equal to momentum squared times c squared. That would just be basically mv squared, right? Plus this rest energy, mc squared squared. The consequence of these two equations cannot be understated. It's that the mass and energy are equivalent and that they can be moved back and forth. And of course, we have horrifying evidence that that is true, right, in atomic and nuclear weapons.
It followed from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is put equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Cockcroft and Walton in 1932 experimentally.
Consequence that the energy of a particle is equal to its energy of motion plus an energy that's stored in its mass. And because c is such a big number, this energy that's stored in its mass is a huge number. You can get a lot of energy out of a little bit of mass. And that's why people look to things like nuclear fusion and have looked to things like nuclear fission as power sources. Okay, suppose our astronaut, as an example, has a mass of 70 kilograms. Compare her classical and relativistic kinetic energy. Okay, this is our astronaut that's been that we have considered in the previous examples. 1/2 mv squared in the case that we've looked at, moving to 100 light years, is, you can calculate, given her mass and the fraction of the speed of light that she's traveling at, that 0.87 c is about 3.2 times 10 to the 18 joules. Her relativistic kinetic energy is gamma mc squared minus her rest energy, or 3.8 times 10 to the 19 joules, so an order of magnitude higher. We could also ask how much energy would be released if our astronaut were completely converted into energy. Well, that's mc squared, or 6.3 times 10 to the 18 joules for the rest energy, just for her mass. If you add the kinetic energy, the relativistic kinetic energy, that turns out to be about 4 times 10 to the 19 joules, or 10,000 megatons of TNT. You get a lot of bang for your buck when you convert mass into energy. Okay, and we'll do plenty of examples in class where we look at these different kinds of conversions. Let's look at one more example. An electron has a total energy of 10 mega electron volts, MeV, as measured in a particular laboratory frame. What is the value of its kinetic energy and its speed? Okay. You'll often see this, right? And we often talk about high energy particles. when we talk about high energy particles, we often measure their particles in terms of mega electron volts. Those of you who have taken chemistry know that chemical transitions, for example, involve electron volts, maybe tens of electron volts. Nuclear transitions often are measured in millions, if not billions of electron volts. So in the rest frame, the mass of the electron times c squared is 8.2 times 10 to the minus 14 joules. That's not a whole lot. Electrons are not that big. And that gives you the canonical value of about half an MeV, right? So 0.511 mega electron volts. Okay, an electron volt is a unit of energy. It's the energy that's required to accelerate an electron through 1 volt of potential difference. Okay, so the kinetic energy is E minus mc squared. Well, we know that it's 10 mega electron volts minus basically a half, so that's 9.5 mega electron volts. The energy is gamma times mc squared. We can solve for gamma now that we know what E is. That's just E divided by mc squared, or 19.6. Right? Gamma does not have any units. The larger it is, the closer we are to the speed of light, as you'll see. So gamma squared is equal to the square root, or to 1 over 1 minus beta squared. And that's 384 if you do the math. So beta squared is 1 minus 1 over 384, or 0.997. So if you solve for beta, that's equal to 0.999. In other words, if you have an electron that has an energy of 10.0 mega electron volts, right? Its kinetic energy is 9.5 MeV. 0.5 of that, of the total energy, is due to its mass. 9.5 of it is due to its motion. And that motion, that 10 mega electron volts, means that its speed has to be 0.99 times the speed of light. The higher the value of gamma, the closer and closer and closer you get to the speed of light. You'll never get there, but you'll get asymptotically close. To accelerate something that has mass to the speed of light would take an infinite amount of energy. Okay? Would require an infinite impulse to change the momentum that much. It's physically impossible. And with that sad note for Star Trek fans, I will end it here. And we will pick it up as we move into different parts of modern physics next time.